Hi guys, welcome to the last video in the spectroscopy series. This video is going to be all about PES or photoelectron spectroscopy. So photoelectron spectroscopy or PES utilizes X-rays. So X-rays are a very high energy wave, which means there's a very high frequency. So high energy, high frequency. These energy waves are actually so intense that they can completely separate electrons from their atoms. So this is all about ionization, taking those electrons away from the atoms. Okay, so just a reminder, it is this kind of X-ray, not this kind of X-ray. Two different types of X-rays. So using the PES, scientists actually identified specific elements by comparing the kinetic energies of the electrons removed to the energy of the X-ray photons that bombard them. So you can actually compare the kinetic energy of the electrons to the photons that are being shot at those electrons. So reading a PES graph, so there's a couple things that you want to look for. And the first thing you want to look for are the number of peaks in the spectrum, because the number of peaks represent the number of electron orbitals that exist in the element. And so the s orbitals, okay, so the smallest peak represents the s orbitals. And remember that these s orbitals have 2 electrons. The full p orbital, which has 6 electrons, would then be 3 times the height of the full s orbital. The full d orbital, okay, that has 10 electrons, would then be 5 times the height of the full s orbital. So the highest energy peaks represent the electrons that are closest to the nucleus, right? That's because the closer to the nucleus, the more difficult it is to remove those electrons. It's being held more tightly by the nucleus, and so you have to put more energy in order to remove those electrons. So with this example, it says to identify the orbitals and the element represented by the PES spectrum below. So the first thing that we want to actually do is look at this x-axis down here, and we want to look at energy. So remember that the higher the energy, the closer to the nucleus. So if we look, okay, typically it's going to decrease as you go to the right. So this is going to be the highest energy. Okay, so this is actually the 1s. Okay, so notice that there are breaks here in the x-axis. These breaks are just to help the scale. Okay, so it's just when there is a break in the scale, just to show that there's different energies. So here we have the peak that is closest to the nucleus. Okay, it takes the most energy to remove. This is going to be the 1s2. Now the reason that I know it's 1s2 is because we have more peaks, which means we have to have a full 1s before we can continue filling. So that means that this line right here represents 2 electrons. Okay, so then we come next to the 2s2. Okay, then notice next would be the 2p. So here's 2, 4, 6. So 2p6. Right, so each line represents 2 electrons. So then we come to 3s2, okay, 3p6. Okay, now notice this has 10 electrons. Okay, well this is actually the 3d10. Okay, and that's because when you're removing electrons, you're removing them from the outermost energy level. So here we then have 4s2. Now notice next we'd move to the 4p. It's half the size of the 4s2, so it's 4p1. So if we look at this electron configuration, okay, let's look at what element ends in 4s2, 4p1. Okay, well that is gallium. So this actually represents the photoelectron spectrum of gallium. So notice that this actually isn't as difficult to read once you know what you're looking for. And this is very useful because this allows us to actually see how the electron configurations work in an atom, and really shows us why it works, and it helps to back up our evidence with ionization energy and looking at the amount of energy that is either required to remove a core electron or a valence electron.